we are going to go over voltage. And voltage is electrical potential energy per unit charge. Now, before we go over voltage, I'm going to give you some applications to what we're doing that we see in the real world, so we can actually see it happening. So the first is, imagine a tree. And in the real world, there's gravity. So we can draw arrows of gravity going downwards. So gravity is like the electric field. We put a charge or a mass in this field, and it's going to experience a force. So mass is like charge. So when we visualize electric fields and voltage and charge, we can think about it as mass and gravity. Gravity is a field, mass is like charge. So let's look at the units for gravity. Gravity is 9.8 meters per second squared, right? Which is acceleration, meters per second squared. And we know that force is mass times acceleration, and the units of force are newtons. Mass is kilograms, and acceleration is meters per second squared. Now let's look at the equation for electric field. We know that the force of a charged particle is the charge of that particle times the electric field that it's in. Units of forces are Newton, charge is coulombs, and electric field is newtons per coulombs. The C's cancel out. So, if you see the comparison, QC is like kilograms or mass, and E in newtons per kilograms is like A, or meters per second squared. Multiplying acceleration by mass gives you force, and multiplying the electric field by a charge gives you force also. So let's draw the tree again. And we'll draw the field, which is gravity, and this is a uniform field because we know that no matter where you are, gravity is always 9.8 meters per second squared for the Earth. And we know that the field, G, equals 9.8 meters per second squared. And we're going to draw an apple. And this apple has a mass of 1 kilogram. So, we know that force is mass times acceleration. So it's mass 1 kilogram times acceleration, 9.8. So we know that the force on the apple is 9.8 newtons. And we're going to say that this apple is 1 meter from ground, our reference point, when we know that ground has a potential energy of 0. Now we're going to draw what we've been learning. Electric field lines. And we're going to say that the strength of this electric field is 9.8 newtons per coulomb. So, it's a field. It's the same as gravity, just different units. And we're going to place a 1 unit charge of 1 coulomb here. And we're going to say that the 1 coulomb charge is 1 meter from what we're calling here is ground of potential energy 0. It's 1 meter away. So we know that electric field times charge of 1 coulomb gives us force. So we know that the force on this particle is 9.8 newtons. Now, in the last class of physics, we often talked about energy, and we know the units for energy are joules. Work equals force times distance. We know that work explains the amount of energy we've used. So the units for work is joules times force of newtons times distance of meters. So, looking at the tree example again, we know that the potential energy of the apple is the force on it of 9.8 newtons times the 1 meter distance that it can fall. So we know that the potential energy is 9.8 joules. Newton meters is a joule. Same thing. Now we're going to look at the electric field. The potential energy of the electric field force is 9.8 newtons. It has to travel a distance of 1 meter. So we know that the potential energy of the charge is 9.8 joules. So we know that the potential energy of this apple is 9.8 joules. And it weighs 1 kilogram. So let's say that instead of this apple here, we had a brick. And this brick weighed 2 kilograms. The potential energy of the brick would be 9.8 kilograms times 2. So it would be 19.6 joules. So we can make an equation. If the apple is always in this position, that'll tell us what the potential energy will be based on the mass. So the potential energy at this point, at this height, is always 9.8 joules per kilogram. So if we placed a 5 kilogram block right here, we would do 9.8 times 5 to give us the potential energy. But the same thing is true for this electric field. And the voltage at this point, where the charge is 9.8 joules per coulomb, because we know that coulomb is like mass. So depending on what charge we put at this point, it'll tell us what the potential energy is. And joules per coulomb is the same thing as volts. Now at the beginning of the section, we introduced what voltage is. And voltage is the electrical potential energy per unit charge, which is what we just showed here.